Everybody's quiet. Still have 1 minute.
So we can make noise. Am I on? Do you hear me? Okay. 1, 2, 3.
Okay, I guess we can get started. Is it okay if we start? All right, cool. So it's my honor today to introduce the colloquium speaker, Ali Hajimiri. Professor Hajimiri, of course, very well known to the community, and many of you here, of course, are excited to hear him talk. I'm going to read his bio, and then I'll tell you a little bit more about him based on my own personal experience. So Ali is the Bren Professor of Electrical Engineering and Medical Engineering, the Director of the Caltech Holistic Integrated Circuits Laboratory, and co-director of the Space-Based Solar Power Project at Caltech. His research interests are high-speed, high-frequency electronics and photonic integrated circuits for applications in sensors, photonics, communication, wireless energy transfer, and biomedical devices. He co-founded Axiom Microdevices, which built a CMOS PA. It's shipped around 400 million units and was acquired by Skyworks. He's a fellow of the National Academy of Inventors. He's also a fellow of IEEE. He served as a distinguished lecturer for the IEEE Solid State and Microwave Societies. He won the Feynman Prize for Excellence in Teaching. That's Caltech's most prestigious teaching honor, as well as Caltech's Graduate Student Council Teaching and Mentoring Award. He's a 3 times winner of the Associated Students of Caltech Undergraduate Excellence in Teaching. Oh, no, did I reread that? He's co-recipient of the IEEE Journal Solid State Circuits Best Paper Award. It's a big deal. ISSCC Jack Kilby Outstanding Paper, also very big deal. Co-recipient of the RFIC Best Paper Awards. 2-time recipient of the CICC Best Paper Award, and so on. So many, many awards. Many of you, of course, know him, and I've actually known him for a long time, about 30 years. So I was a grad student here at Berkeley, and I worked with him at Bell Labs over the summer. We shared a house, so known each other for a long time. So I've some funny stories about him, but maybe that's for another time. Actually, I'm surprised it's not in his bio. He really should add to his bio that he is like the academic, like the, you know, he's basically the advisor of probably half the professors in our field, at least all the good ones. So if you go into industry, if you go into any good university and look for the faculty there, you'll find that either Ali was the direct advisor or indirect, like maybe one level of indirection, the academic grandparent. So actually we have one of his grandchildren here, Aditya, who we hired recently, is actually worked with Ehsan Afshari at Michigan, who was Ali's student. Many people, Hossein Hashemi, let's see, Kaushik Sangupta, Aydin Babakhani, we mentioned Ehsan, Donnie Ham at Harvard. We just talked about Jim Buckwalter at Santa Barbara, many, many people. So on his website, there's an interesting academic genealogy. You can look and see all the connections. So it's great to have you here. Thanks for coming, and we're looking forward to your talk.
Thank you very much. Thank you, Ali, for that gracious introduction. And you know, yes, Ali is right. I mean, we share the house, so that way you get to see the person from all sorts of different angles. And you know, Ali was always the calm, kind of like relaxed voice, sound of the reason. So I'm honored to be here giving this presentation, and I was debating between 2 or 3 different talks. Actually, I have all 3 sets of slides open on my computer. I decided to go with this one, because I thought this is probably more cohesive, one subject. My group does work on a lot of different topics, but I decided to focus more on one aspect of things more than others, and this is about working in concert. And some of the concepts many of you in the beginning will be familiar with, but I'm going to show a demonstration of how this is applied and how this is going to turn into something. And obviously, the most important thing to say is that, you know, as professors, we come and present a lot of work, but it's really the work of students like you and postdocs and people like that. So I would like to say that although I may not be able to credit every individual contribution on every slide to every individual person, but it's the work of a group of people. I'm the cheerleader, I'm the presenter, I'm the front man. Other than that, the rest of them are the work of these people. So, okay, so how do we communicate with each other? If you think about the ways of communicating. The reason you see me or hear me is that we can use waves, right? Waves are critical to our long-range communication. There's nothing in the way of your presence and my presence being felt other than waves. And waves are very critical, and as everyone probably in this room already knows, waves have this interesting property that, we put them together in phase, and then you get a larger wave. It can carry more energy. And they can come out of phase, and it would carry less energy, or you can actually, in principle, be canceling out. So this is the basic principle that goes to the concept that has been known for several centuries now, the concept of interference. So the analogy I use is that if I go and sit at the edge of a pond and start putting my hands into the water and moving it up and down, moving them up and down, you would create a set of waves. And as everyone here who is familiar with physics knows that there are some directions where you get more energy and there are some directions where you get less energy transfer. So this is the concept. So now, and this really goes back to the question of how can you extend this? And this is something that, again, is very well known, has been known for a long time, the concept of army of mice or army of ants versus the big elephant, right? There are things that a large number of elements working together at the same time can do that a larger unit cannot do and perform. And this is something from old times. And this is really the concept of multiple hands. And some of these faces are a little bit younger than who they are now. So this is where we went, and then we sat at the edge of a pond. Instead of 2 hands, you are using multiple hands. And if they're all going at the same time, you go 1, 2, and just we go all in the water and come down. We create a wavefront, right? So we basically create something that where most of the energy is concentrated in one direction. Again, this is something that's very well known, very well understood. But this is the way it works. If you have multiple sources that go synchronously, you can get basically the energy transferred in one direction. And the other thing that follows this naturally is that, okay, now if you can do this, the timing of this thing is everything, right? And since the timing is everything, in terms of where the energy goes, by controlling the timing, you can also control the direction. And this is the concept of phased array. I mean, it has been around for a very long time, that you can actually send the energy in various directions by controlling the timing only. And this is where we ran this experiment, and you can see there's a wavefront created here at an angle where we give each person a number, and you can see that the wavefront is going at an angle as opposed to going straight down the pond. So you can see that if the wavefront is over there. So, and this is basically what you can do. Now, you can do a little bit more than this, actually, when you have this thing. And what you can do more than this is that now, again, by controlling the timing of this thing, you can actually create 3-dimensional focal points. And this is the focusing aspect. So this goes beyond just far field beamforming, because beamforming is a far field concept. It's a Fraunhofer concept, basically, Fraunhofer range of things. But you can actually have a Fresnel region operation, basically radiative near field. And by controlling the relative timing, you can create points where you act like a magnifying glass. And again, the key here, like comedy, is timing. Right? In comedy and life, timing is everything, right? So now, the thing is that by controlling the timing, you can change the 3-dimensional focal points of this thing. So now, how is this useful? It has applications in many things, but we'll focus in this talk on one, which is the energy transfer. So if you think about our world, we've gone over the last 20, 30 years from wire to wireless in communication, right? I mean, some of you may be old enough to remember the times when we had dial-up and Ethernet cables, and we use them, and now we don't, and for the most part. And a lot of times, actually, these systems are pretty fast. Even like if you use an Ethernet cable, it's quite a fast system, but you don't use it because of the convenience of the wireless activity. Same thing with sensing. A lot of it has gone wireless as opposed to wired. But the power really is the part that has not gone wireless. So if you think about your phone, for example, most of its function are wirelessly done, except for charging. That has to be either done by contact right now. I mean, direct connectivity or contact charging, which I don't count as wireless energy transfer, at least long-range wireless transfer. Yet there's no wire technically, but it's contact. And the applications, what are the applications? You can think about things that can happen on Earth, in this room. You can power devices, various wearables, things of that sort. Or you could think about longer range that we'll talk about. And there are various sectors of applications for something like this. So you can think about using it in all sorts of sectors of, and this is not an exclusive list, where you have energy. Anytime you have a battery or a power cord, you are thinking about being able to benefit from wireless energy transfer. So that's something that's in there. And there's something that's more fundamental, I think, to this in terms of, if you go back to this previous picture, is that one of the things, if you think about what made it possible to be able to store our data on the clouds. If you think about this, 20 years ago, 25 years ago, we had to carry most of our data with ourselves, either on our hard disk, hard drives, or some carry it somewhere now. And nowadays, we don't. A lot of our data resides on the cloud. But why is that possible? The possibility comes from the ubiquity of wireless access and wireless connectivity. If you didn't have ubiquitous wireless connectivity, you would not be, cloud solutions would not be a viable or useful solution. Now, if you extend this argument to energy, let's say if wireless energy becomes ubiquitous, then one could argue that you don't need to carry as much energy with you. And most of the volume of our devices are taken up by energy storage volume, which is the battery. So that's the question of the changing the nature of the thing. So the devices can become smaller, your batteries can become smaller, or battery-less even. And I'll show you an example of something that doesn't have a battery and operates and all those things in a second, in a few minutes. And we'll talk about that. But before we do that, so the question is that also one question that comes up is that, okay, what is the nature of these things, what wavelengths you can use? And we know that millimeter waves and RF signals basically fall in the category of non-ionizing radiation, which basically means that each photon doesn't have enough energy to cause chemical change. Unlike ultraviolet light or higher energy like X-ray and things of that sort, which each photon has sufficient energy to knock an electron and kind of change the molecular structure and atomic structure permanently, the low energy photons basically create vibrational, excite vibrational modes, and you generate heat. Now, of course, a lot of heat can cause damage. That's true. But the thing is that it's a different kind of thing. The same thing that you get if you stand in front of a heat lamp. So that's one thing to keep in mind. So now let's talk about this focusing concept that we saw visually. But the question is that how can you think about it a little bit more analytically? And one of the things you can have is that you generally think about two arrays. An array of transmitters, a generator unit, we call it GU for short, a generator unit, and an array of recovery units or receiving units, RU. And each one of these things, let's say to transmit, so you adjust the phase and timing of each one of these elements so that the focal point is formed where the receiving unit or RU is. So this way, you can actually transfer some energy from GU to RU. And the question is that what are the limitations, what are the constraints, and what are the factors that come to play in something like this? So one of the things is that we have this definition of Fresnel and Fraunhofer regions, near field and far field, radiative near field and far field. And where does that come from? If you look at it fundamentally, people write down sometimes just like, oh yeah, it's this and that, or 6D, D, or D squared over lambda, or 2D squared over lambda, or something like that. Where does this come from? It comes from basically an assumption about how much phase variation can you tolerate across different points of the transmitter, typically, when you are at the receiver. Meaning that different points on the transmitter, how much phase difference the signal launched from those will experience by the time it gets to the receiver. Now, and that implicitly assumes that your receiver is very small. If you want to refine this you want to change this definition of near field and far field to account for both the transmitter, generator, or receiver, or transmitter and receiver, to have finite size, basically then you come up with something like this, which basically says that the R pi over 8, which basically means that if you want to have no more than pi over 8 variation of the phase, becomes proportional to the diameter of the transmitter, diameter of the receiver, and inversely proportional to lambda with some factor of 2. And this is like the factors you can play with. And now, this basically defines the boundary of Fresnel and Fraunhofer, where we are radiative near field versus radiative far field. So if you think about radiative, and these are two examples, and both these two examples are chosen to be relevant, so they're not completely random to the discussion to follow. So let's say you have this is a kind of arbitrary one. So let's say you have a 30 centimeters transmitter and a 30 centimeter receiver diameter. And this can change because the product is what matters, the ratio. And then you have an operating at 24 gigahertz for the sake of argument. What is the distance at which you leave the Fresnel, the radiative near field, and go to the Fraunhofer? And we'll see this is important. And that range is in like 14, 15 meters. Now, the second example, imagine that you have a transmitter that's about 1 kilometer wide, a receiver that's 1 kilometer wide, and you're operating at 10 gigahertz. And the question is, what is the r pi over 8 in this? And this is like 70,000 kilometers. Just to give you a sense, geostationary orbit is 36,000 kilometers. Just keep that number in mind. So now, and then the other thing, of course, is that what is the diameter? If you try to focus it, how much you can focus it? Again, basic physics. The diameter that you can focus in is on the order of the range, proportion times lambda, divided by the diameter of the transmitter. So if you want to focus it more, you need either a larger diameter in the receiver, or you need to be shorter range, or you need to be at a smaller lambda. So you can see, for example, with something that's 30 centimeters wide, at a distance of 1 meter, you're looking at a diameter of about 6 centimeters. So this basically defines different regions of operation. So it means that if your receiver array, so just imagine that this like 4x4 grid represents your receiving array, where you're focusing your energy, right? If you're close enough, your beam of energy can be smaller or about the same size as this. And in that case, you recover most of the energy, at least not recover, you have most of the energy that's in your main beam is at least intercepted by your receiver. And that's this region of thing. Now, this number is 100% of that beam, which is like 87%, 83%. So that's not, let's not get hung up on the exact 100%, but I'm saying that it's 100% of what is achievable from the main beam. And then once you get far enough, as you get far enough, the spot becomes larger. Even when you optimize it, this is basically just diffraction limit. At some point, that spot size becomes larger than your RU. And at that point, the farther you get, the more you lose, because you're capturing intercepting a smaller fraction of the thing, of the spot, because the spot is getting larger as you get farther away. And of course, this trade-off depends on the wavelength, which means that if you go to higher frequencies, it gets better. So if you look at the first order approximation of efficiency, that we call it transfer efficiency, it is the area of the transmitter, area of the receiver, divided by the distance squared between them, and the lambda squared, wavelength squared. So this is like first order approximation of efficiency. And of course, this is valid once you get into this region, because if you go to R of 0, efficiency doesn't become infinity, obviously. So there's like more detailed expression. So that's why we, over the several years, we actually started developing, when we started developing this phase array for energy transfer, these are the 4 samples of these things at 4 different frequencies. So we started off with making arrays, and we have big arrays in my lab, legacy stuff made out of these things at 2.4 gigahertz that did wireless energy transfer more than 10 years ago. And then this is like a 5 gigahertz system where we develop our own little chip here, and then we had stuff around it. And then this is the 10 gigahertz system. These are rigid stuff. And then we went to 24 gigahertz system. And you can see it, the same 2x4 obviously becomes smaller and smaller, as you expect. And the other thing about energy transfer to keep in mind is that unlike other applications, you cannot afford to have a sparse array. In communications, in MIMO and all those things, you can afford to have a sparse array, meaning that array that's not fully populated. And this is actually called the sparse array curse, which means that unless you have an array that's substantially on lambda over 2 scale, maybe a little bit larger, a little bit smaller, things of that sort of spacing, then your energy starts going in other directions, other than the primary direction that you're interested in. And unlike communication, that lost energy is a major hit. In communication, you say, well, yeah, I don't care if I do 6 dB of my power to the side lobes and all those things, as long as my signal gets there and I recover my data, who cares, right? But for energy transfer, you do, because you don't want it to go. So that's why you need to make sure that the lambda array is dense. Now, getting a little bit into the way to think about it, and I'm not going to get into technical stuff, but if you're interested, I can guide you in the right direction. We've done a lot of analysis of these things and theoretical side of it. But if you think about this channel of this multiple transmitter, let's say G by G array of transmitter, and R by R array of receiver, you can think about it as like a multi-port network, the space and transmission and antenna, right? And if you look at this model, you can actually express your efficiency in terms of those parameters as a matrix form and all those things. And from that, you can actually extract a model that is general. You can actually emulate any combination of arrangements of these things, different angles, different positions, things of that sort, and you can verify that this is correct. And once you extract this model, then the rest of it, which is a nonlinear process, you can model differently. So you can actually break it down. But now, how do you achieve this focusing? So one of the things that you need for achieving something like that, a focus like this, is the ability to detect, so the one way is that, let's say, it's a very simplistic algorithm. Let's say I'm sitting here and I have n transmitters and I have a knob on each one of them. I can adjust the phase, right? And what you do, let's say I'm transmitting some power to somebody in the back of the room, and somebody in the back of the room is sitting there and say, okay, how much power are you getting? You say, hotter, colder, hotter, much hotter. So you're sending me information back about how much power you're receiving. The question is that with a system like that, can I find the optimum phase setting of all the elements? Is it possible to find it? And the answer to that is, in principle, yes. So let's talk about that first and then come back to the numbers. So this is one of those knobs, right, in the array. And you're sitting there, and in principle, if you sit there and tell me, oh, it's hotter, colder, because this is actually a linear combination of these things, I can keep it on the hottest setting, and then move on to the next knob and keep turning it till you get the hottest, and then go on and on and on. No, it does actually. But it doesn't, yes. Well, in principle, yes, I think we are in agreement. In principle, it does work. But in practice, the problem is that once your array becomes large, it is not going to be, it's not going to be visible. Because the fluctuations that you get in this, and this doesn't need to be very large. This array can be, I don't know, 32 elements, 64 elements, and you start losing this information. And we're talking about much larger arrays, as you will see later on. I'll show you some much larger arrays. Now, the other thing is that, yes, that in principle works if these were independent, but if what happens is that if these elements are, if you think about all the combinations, this is an astronomical number, and people like to show astronomical numbers and compare them with the number of atoms in the universe and all those things, and let's not do that. So, but the essence of it is that now, let's say there was no phase or variations of angles. What happens is that this space by itself, this search space, if there were no noise, this space is actually a cycloconvex space, meaning that you can arrive with a gradient descent or a variant of gradient descent at the optimum solution, assuming that there is no fluctuations of that sort. But the reality is that because of the noise, we can't do that. So the question is, what happens is that if you have one element out of the many, this becomes almost flat, and then now you're sensitive to noise, the space of search, where you're looking for. So how do we solve this problem? How do we get around this problem if you wanted to use this method of getting feedback from the user, the receiver? Well, one way from an algorithmic perspective is that what if you could turn, let's say, change half of the array with respect to the half of the other half of it. So let's say I have some arbitrary phases. I don't know what my phases are. I start changing them with respect to each other. I know I'm going to get a large interference pattern, right? I'm going to either can do it digitally or can analog. I can get large changes in the receive. Because if I mess up with phases of half of my elements with respect to the other half, everything is going to change. The bottom line is that, but then I'm going to lose information. I don't know much about what's going to happen within these elements and how each one of these can be set. So it means that I need to have more information, so I need different patterns of changing these with respect to each other to be able to recover that information and get that. So in essence, what you really need is a basis, right? If you think about this as a vector space of n variables, or n-dimensional vector space, you want a basis that spans the space, right? So you want a basis that spans it, and then I would argue that you want, ideally, this basis to be orthogonal, or near orthogonal. And the reason for near orthogonality need for something that's of that nature is that you want it to be able to operate this in batch. So instead of telling me every time how I'm doing, I run through all of my things at once, and you collect that information and send that back to me, and I can process them independently. And the more orthogonal my basis is, the better I can do this. So you can create these bases, and this is an example of one of those bases for a 2x4 array, 4x8 array, sorry. And you can see this is a complete span it spans the space completely, and it's orthogonal, and it's based on it's basically an inner product of different rows of Hadamard matrices. So mathematically, you generate it that way. But you can use these kind of things, and you can focus it. And what it does is that it allows you to move in different directions. And it's interesting because the most basic form of this basis, a 2x1 array of this one, is something that all circuit designers are familiar with, but they don't refer to it. So The breakdown of one that's 1, 1, and one, the one, so imagine only 2 by 1. The first one is 1, 1. The second one is 1, negative 1. It's common mode and differential, right? So that's the most basic variant of this more general concept. So yeah, so this is basically what the way that algorithm works. But then there's more to it, right? So you have to be, and one of the things that we do, we started building these things on chip because there's a lot of stuff that needs to go on. So I'm not going to get into the detail of the ICs and the circuits and what's going on. So this is an example of the 10 gigahertz system, that chip that we built that has like 16 different drivers and PAs and outputs and signal generation. So the way it works is that a low frequency reference signal comes in and it's synthesized, and high frequency stuff is synthesized from that reference. And everything else is generated. 10 gigahertz system is generated off of that. All the phase control, everything is happening on that. So what I'm going to do, I'm not going to go into the details. I mean, there are I have like several slides of details of the circuitry, but I'm not going to get into that for the seminar. But what I'm going to show you is that, well, eventually you can make, this is the picture of the chip, and then you can make a board, and these are rigid stuff. That we did this several years ago. And you can make it large arrays, not super large, and we'll get to the super large soon. And then you can see that you can actually see the focusing. So what you see, for example, is a measurement. You can see that there's a focusing happening. There's a focal point where the energy maximum. Of course, it spreads out. And once you have a receiver there, you see that most of the energy is absorbed. And these are actual cross-sections of the measurement of the system. And you can see that it kind of follows the general trend that we had expected. So nothing surprising there. So we make these things, and then eventually one of the things that we do is that the ability to create these things gives us the ability to generate spots. So this is an example. So what you see in the back is an array of LEDs, antennas attached to LEDs. There are no batteries or something. You can see that we have actually formed 2 spots in the same array transmitter. And what you saw before that was that there were 2 receivers, 2 of these RUs that are powering these LEDs, and actually the energy is recovered in DC. So you can see that you can very selectively send the energy only where you need and nowhere else. So that's one of the things that you can do. And there are more examples of this thing, and some of these are from a company that I started, so just like a co-founded, and this is an example of maybe how small you can make these things, and the ones with the lights. Get rid of the inspirational music. But anyway, so this is, for example, you can see how small a single receiver can be, and it's like being transmitted. You can send power to it and transmit it. And there are all sorts of variants of these things that you can make, large, small. It can do multiple things at the same time. There's another one maybe with the, maybe I can show you. Another one with maybe the lights that you can see. Let me just get rid of these. So you can see, for example, one here that's wirelessly powered. You can move it. It's right now, basically, that you can see that the energy is not there. The system finds it and focuses on it. Then there's one with 2 of them and things of that, so you can see. Now, the other thing that I mentioned, something that's a battery-less system, right? And here's a battery-less drone. So, and it's translucent. So you can see there's an RU, and we take the translucent one, so you can see there's nothing hidden inside of it. There's no trick. So this drone is actually flying with wireless energy. And this is from several years ago. And now we can fly much bigger drones, not only fly, power and charge at the same time. We have more power than the drone needs, so we can actually charge the battery at long distances. And this is another one, another very older one. So again, this is old. This drone is being charged actively. And the other thing that you can see is charge and drone. But the other thing is that you can see that these spots that are formed, these are, you can say, form multiple spots at the same time. And you can see basically just send the energy where you need it and send it as you wish to the right direction. So these are a couple of examples of how something like this. And then this was a few years ago, and recently the company announced that they have made the world's largest phased array. So this we believe, based on whatever we know, this is the largest ever phased array built with more than 70,000 synchronized elements that we know of. The largest one we know, I think, is like something 15,000 to 20,000 for some sort of a military phased array. At least to the best of our knowledge, that's the largest number of arrays, more than 70,000 and more, and then some. And then this kind of systems allow you to transmit a fair amount of power. So that's one thing for terrestrial applications and all those things. But now, let's go a little bit crazier, right? If you want to go get a little bit crazier here, what we can say is that, well, what if we do take the photovoltaics, put them in space, and transfer that energy wirelessly to Earth? Now, the first question is that why on earth would you do something like that? And why would you not put those photovoltaics in the Mojave Desert and connect them to the power line? Valid question. We'll get to that in a second. And now, but before I do that, this is not a new idea, by the way. We were not the first crazy people. There were other crazy people before us. But at least they were writing it in science fiction, not science. So Isaac Asimov has actually a short story from 1941, The Reason. And the story is actually about a robot on a space station having an existential crisis about who it is and and what its purpose in life is and all those things. And the human operator on the station tells him that, look, you're on a space station outside a planet, that those bright spots that you see, that bright disk you see over there, that's it's sun. That's the sun, and that those circles are planets, and you're taking the energy, converting them, and microwaves transmitting them to Earth, and it's explaining it space solar energy, right? It's the description. And at the end of this kind of description, the robot responds and says, do you expect me to believe such a far-fetched notion? What kind of a fool do you take me for? So even the robot has a problem believing something like that. But OK, let's talk about it. Let's say, why would you want to do this? So the first thing is that you have to realize if you're at a high enough altitude, you don't have day and night, you don't have clouds, and you don't have the angles of the sun and the seasons. And if you take that, and you can actually do this calculation, and I convinced myself, I've done this calculation myself, to how much on an average, how much more energy do you get in space? And it depends on which city you pick. If you pick London, you will get a factor of 14. If you pick Mojave, you get a factor of 4. On average, it's a factor of 8. So you get a factor of 8 to 9 more power, and you get it consistently. The biggest problem with photovoltaics on Earth is that they don't generate power at night. So it means that you also have to have storage. And on top of that, you can have clouds and things like that. So there are other advantages. The thing is that especially if you have some sort of a phased array-based system like what we described, you can actually dynamically send it to the desired location or to multiple locations like those demos that I showed you did exactly show. So the bottom line is that if you have something like this, you can send the energy where you don't have the infrastructure or the storage for the power. So that's the important thing. And then there's higher land utilization because the conversion efficiency of the, and I'll talk about this maybe later, of the RF signals to the DC are much higher. But now, so if this is such a great thing, why haven't people done it yet, right? There are many different reasons for not doing it. Space stuff is expensive. When you launch things into space, it costs dollars, plural, per grams. Right? To launch, and depends on which orbit you go to and all those things, the price can change. The other thing is that this structure by nature has to be large if you want to collect sufficiently large amount of power, so photovoltaic energy, right? I mean, you have a certain amount of insulation in space, you have close to 1,400 watts per square meter, something like that, on the best of condition. So, and that means that the structure has to be large at least in 2 dimensions. And then if you are trying to transmit, you need to have a large enough aperture from the calculations that we had to make sure that the spot is sufficiently small that you can actually recover it from a reasonably small spot. So all of those things point to the large dimensions. And large typically means heavy. And the other challenge is that and this is the way it has been envisioned in the past by other people. There are variants of this thing there are more variants of this thing that people have envisioned in various forms and all those things. And all of them are basically taking 3 different technologies and put them together. They're taking bits and pieces and connecting them, say, well, I buy photovoltaics, I buy a giant dish antenna, and I buy a bunch of wires and a massive microwave transmitter and transmitter. And of course, it doesn't work that way because it becomes heavier. But the question is that, is there a way to rethink this? Is there a way to possibly evaluate this in a different way? And one of the ways is, what if you could make these out of very thin structures, sails-like structures, that you deploy in space? Because otherwise you need space assembly. And they formation fly, or you can be single unit. And you have photovoltaics on one side or both sides, and you have RF transmitters on the same side. And you do not aggregate the DC power from the photovoltaics. You transmit it on the spot. If whatever energy you get, each element transmits that energy. So it eliminates the massive mass of all of this aggregation of power and all those things. And you have to make it lightweight, and it has to be safe. So if you want to make it lightweight, and if it has large area, those are the two constraints. It can only mean one thing, right? Something that is large in X and Y, and it's very light, has to be very thin. And furthermore, if it's supposed to kind of like be able to be stored on a rocket fairing that's not gigantic, it means that it has to be something that can be rolled and packed. So you have to be able to pack it, roll it, and unfurl it in space. Then you can put a bunch of them in a fairing of a rocket and launch them in space, and then form your space station. Now, so this means that it has to be light, which means that it has to be thin, and it has to be flexible, because it can need to be rolled and packed. So those things limit the kind of things that you can do. And then there are other constraints. For example, you need to know the solar installation is fixed. Your angle can change, but it can only make it smaller. Cosine of theta is not going to go over 1, right? So what happens is that your angle, so you have a certain amount of insulation, and depending on your choice of frequency, the power per element is going to be determined by that, fixed. So the higher the frequency, the more you will pack in one area, so the power per element would go up, would go down, that you need to transmit, and those are the constraints that you have. So these things, eventually, and the vision is that these things will be formation flying. And of course, this is obviously not to scale, because this thing is not going to be larger than the planet. But just to give you the concept of these things. But so how do you do that? And this is the next couple of slides about this. These two next slides are the work primarily done by my colleague Sergio Pellegrino, who works in space structures. And they have developed very interesting and clever ways of using origami-like structures to be able to fold these things and unfold them in a way that is conducive to having all of these complex structures and electronics on the same thing, and then using that and deploying it in space. So this is some of the work that they've done. They've created the structures, and they work very interesting things. And on our side, one of the things that we've done, we've developed this very lightweight phased array transmitter. So this is the antenna sheet, for example, for one of the kind of the earlier generations of this thing. So you can see that these are very lightweight. It wouldn't fit in my backpack, otherwise I would have brought one for you to see, just pass it around to just play with them. And then there's an electronic flexible sheet that goes with it that I also could have brought, but I didn't. And then these things, of course, have all sorts of applications. You can think about these flexible arrays, flexible stuff. That's interesting. But then one of the interesting things is that you have this building block. You can make these, and then you can scale them up. And now to give you a sense of where we are with mass, with that generation. So we are right now around, so what I showed you is like around 600, if I'm not mistaken, 670 grams per square meter. That whole system, including the photovoltaics. And then we've already done something. Right now, we just had something that we are trying to submit to get published. And that's like around a few hundred grams per meter squared. But we think that basically looking at the fundamental technology, we can bring it down to about 80 grams per square meter. And that's what we call an asymptotic goal. And asymptote is an interesting concept. You can try to strive for it and get close to it, but you can never get to it. But to give you a sense, that is lighter than the lightest, about as light as the lightest grade of paper. So in terms of doing that. And these kind of structures are interesting because now these are examples of actual systems that function. So you can actually say flex them. This has both layers in it. You can take a bend, they flex. This is like an earlier design, which had this like pop-up patches, things of that. So we have a different version. But now, this presents a different problem now, right? So now you have a structure whose shape is not constant. We said timing was everything, right? But now you are in a situation where this thing is flimsy. It's very, very thin. So it can basically change its shape on conformation. And this is another version with like pop-up antennas. So we have all sorts of variants of this thing. But so what if it changes its shape? Then all of the phase information is messed up because the phase information, phase setting that you had worked for a certain shape. The shape changes, all of the phase setting need to change because the timing is changed. The time of arrival will change. So then we developed another set of solutions which basically allowed us to reconstruct the shape of the array by measuring the array measuring itself. So basically each element that has a transmitter we built into these chips a receiver. And all they do transmit to each other, and they do the measurements from each other. And from those measurements, it's a very interesting algorithm, and I don't have time to get into it, but there are different variants of this algorithm. So this is a one-dimensional demonstration of different shapes, and you can see that the black is the ground truth, and the red is the reconstructed shape. So the array, solely by its own measurements of its own receivers, and the algorithm that goes into it, can reconstruct its own shape. And these are for concave structures, and these are for convex structures, 1D, so you can see that. And there's some weird structures that this is the first algorithm, and there's a second one that's even better. That's going to come up in a sec. So that they can reconstruct it, and sometimes it just gets confused by some of the weird stuff, which we figured out how to deal with later on. And then you can do it at different frequency with different chips. This is the 10 gigahertz version of that, and it's something. And then this is an example to demonstrate this. So we real time. This video is not sped up or slowed down. This is real 1x speed. So this array is being dynamically changed as a demonstration, and while it's active and transmitting. And this is what you get without the correction, self-correction. You see the power goes up and down on the receiver, as you expect. And the blue one is what you see when you have the correction. You see this becomes a lot more stable, even simple. And then what we did, we completely restructured the algorithm. Now we made it on a much more complex, or much more sophisticated, I should say, way of thinking about propagation on the surface and surface modes and all those things, which I'm, again, not getting into. But what allows us is to kind of do 2D shape reconstructions, purely on the spot, in situ, without any feedback from outside, of the array shape. And you can see that it actually, for all these kind of different shapes and forms, you can see many of them, they can be, this is the first row is the truth, the second one is the reconstruction. You can see that the shape can be reconstructed without any tweaking. Once the algorithm is done, we just let it run on these different shapes, and we see what it generates. And you can see, and there's different amounts of errors. Sometimes it just not is exactly right. So some of these more complex things, we call it tortilla chips XYZ because of the funny shape. Yes, exactly, right. And then, so you can see that you can actually reconstruct these things. So this is also an important thing. And then one of the things that it does is essentially an actual array that's transmitting. You can see that it's forming a spot. You deform it, everything falls apart. But after refocusing and reconstruction, you can actually get the beam back immediately. And you can do this fast enough. So this is another part that needs to go into making such flexible systems work. But there's another problem for making something like work. And that is the timing synchronization. Timing synchronization of arrays is a non-trivial matter, and especially if you have such a large array. I said we have the 70,000 elements array, but this is a much larger array than that. And they're free formation flying free. So to give you a sense of how much accuracy you need for this timing synchronization, you need to have, and the calculation is here, but you need about less than 3 picoseconds, about 3 picoseconds of timing precision across a kilometer distance in space on a flexible structure that is free formation flying with other structures. They're not mechanically connected, right? And just to give you a sense of how small what 3 picoseconds is, light travels less than a millimeter in that time. Light travels less than the thickness of your nail, probably, in that time. To give you that accurate sense of that time. So now, how do we do this? How do you even go about doing this? So it has to be done in a hierarchical fashion. There has to be done in different layers. And one of the things is that you can have a primary beacon and timing reference, which is wirelessly distributed. And that allows you to account for some of the general global time differences because of the different positions. Now, and then on top of that, you have within each one of these modules, which can be between 20 to 50 meters across, you have fiber optic distribution. I'll talk briefly about that in a second. And then within each unit of about a couple of meters, then you have electric transmission line distribution of this timing. And all of them in combination allow you to do that. Now, one of the things that a lot of things are very challenging, but there's one thing about space that's very interesting and useful and good. The orbital dynamics are extremely predictable because you don't have things that make them generally even less predictable, like drag and all those things. And orbital dynamics of objects are complex, but deterministic for the most part. And that also plays a role in a lot of these things and how do you manage these things. Now, about this fiber optic distribution, for example, we developed made these other additional chips, the chips that we made, that actually where the fiber optic comes straight onto the chip. And we have a photodetector on it that detects the light, converts it to electrical signal, we recover it, we sync to it. So basically this allows you to synchronize your elements to this fiber optic directly. So you can actually now use this as a reference point, as a receiver for a center point where you distribute the timing. And to demonstrate that, we have actually, this is an example of two of these arrays, 2x4 arrays, that are connected through 10 meters of fiber. So they're optically and electrically, they're 10 meters apart. Right? But we put them close to each other because we want to do the measurement of their coherence. So when we put them close to each other, their coherence basically is measured over this distance. And what we can see is that this coherence actually allows you to, as you increase the number of modules, you get the power gain as you predicted and expected. So we said, okay, well, we have all of this stuff and all these interesting things. So we said, look, we've made all of these things. Does it really work in space? This flexible, lightweight stuff. Can you really make sure that something you make like this ends up not completely getting destroyed in space? Can it handle the harsh environment of space or the chips and all those things? So we had a demonstration. We said, okay, well, let's try to run an experiment. Let's actually put something in space. And we put together some system, different experiments. And one of these experiments was to put some of these flexible arrays exactly in space and try to do wireless energy transfer in space that hadn't been done before. So the idea is that you made a very small size array, not a very large one, obviously, but we called it MAPLE. It's some sort of a made-up acronym. And then we put it in there, and then we launched it into space. So we actually ended up going to Cape Canaveral, and
2, 1.
Now you know.
Oh my God, it's going.
So it's interesting to us. It's not interesting to other people. So well, yeah, it's what the rockets being launched. Okay, big deal. Okay, fine. Yeah. Anyway, so these are the three amigos or whatever, like the three musketeers. So Harry, my colleague, works mostly on the photovoltaic development for lightweight structure. Sergio is on the space structure, and I work on the wireless energy transfer part of this thing. So this is like a picture from space. So we basically did wireless energy transfer to some of these local receivers to just demonstrate that these things function and perform, and we ran. So this is the part that is easy to talk about, and easy to do relative to the 9 months that followed that we did all sorts of tests and experiment and stress tests of these things, and to demonstrate that, okay, well, how does it degrade over time in space? What happens to it? What are the things? And we did a lot of studies, and we published this too, so if you're interested. And then one thing said, okay, well, if you're doing something like this, then the question is that, can we also maybe point it to Earth and see what we get? Now, the amount of energy that you recover because of the small array transmitter and the large distance and the small recovery area, it's going to be minuscule. But the point is that, do you get the right amount that you expect? Yeah. And that was an experiment we ran on the roof of our building, and we set it up, and then we looked at it, and we had the signal coming in, and then we said, okay, yeah, we are getting exactly as much as we are expecting to get. And so that was good, and we were happy and kind of cherished it. And then, so this is basically what happened. So this is when it went over the thing, and we made some nice animations to show that, okay, yeah, it went over us, and then we transmitted, and then we saw the signal coming in. So, yeah, and then, yeah, we were happy, celebrating on the roof and all those things. And then somebody decided that they want to make a movie about it, and the documentary. So anyway, so that's the. But now the point I'm trying to make, and I'm trying to wrap this up, so and we'll be open to discussions and questions afterwards, is that really I think the more important point is, where's the? Okay, no, it's not functioning. So that wireless energy transfer at distance, I think, is too compelling a technology to not find a place. Now, where that place is, we'll find out. There are very different possibilities, and we are exploring all of those things. And I think there's a large range of options for this, but it is a compelling technology. It actually works. And I think it's bound to happen. Now, would everything become wirelessly powered? Probably not. Would nothing be wirelessly powered? at a distance? Most likely not. Somewhere in the middle, something will happen. And we are excited about that. And this was an, oops, I don't know what happened here. Too many. And this was a demo that we did for our earlier tiles, an example under on a solar simulator. And then this is basically what that was. And then with that, I'd like to stop and let the audience ask me questions. Questions? Yes?
Thank you for the nice talk. I was curious how much power is lost versus how much power is transferred, like in peripheral circuits or whatever else is needed to make this array work.
Right. So that's a great question. That's a very fair question. So here, I'm going to break it down into different pieces. And then we can look at the overall, and I can show you something more specific for the space solar. So the energy transfer itself, so first there's a conversion from DC, let's say, to RF, to microwave. That efficiency, based on what we've seen and what we're doing, can be up to 50%-ish. Okay? So you lose about half of it there. Then you have the transfer efficiency, which is a function of arrangements and distance and all those things, and size of the transmitter and receiver. So there's not a fixed number. But let's say if you are within the right size and the right Fresnel region and all those things, you can get like 80, 85%, 83%, something like that, depending on how you compute your main low power and all those things. And then there is a recovery efficiency, which is the, that's actually pretty decent. That's pretty like 70, 80%. And that's, by the way, one of the advantages of having that on Earth as opposed to photovoltaics, because for the same area, and if you keep the same power intensity as the sun, you will get 4 times more energy per unit area. So, so it's a product of those 3. But if you want something more specific for the space solar, I can show you the Sankey diagram. So here's the so the solar, and by the way, this includes, by the way, the photovoltaics loss. This includes everything starting from the insulation. So insulation is 1367 watts per meter square, 1400, let's say. You're engineers. So now, about 30% of it is reflected on the surface. There's about 50% of power lost into heat. DC power is about 20% out of the PV, let's say, on average, realistically speaking. There's about, if you take all the overheads and all the things into account, like 8.8, but this is for the space one. The ground ones are a little bit better than this, but I'll just talk about this. Excuse me. And then this is the received power, this is RF power, this is the amount of power incident, and then rectified power, which is a fraction of that. This is the incident power on the receiver, rectified power, AC power if there's a conversion from DC to AC, if you want to connect it to the power line. And you get about more than 5% of the fission. So you say, oh, this is minuscule, this is nothing, right? 5%. Okay. But think about the regular photovoltaics on Earth. A regular photovoltaics on Earth give you 20%. Plus these additional losses, because you have to still do the conversion and all those things. So you get less than 20%, you get 15%. But you have a factor of 8 more power, because you don't have the day and night at one. So if you think about it, this is equivalent of a net 40% efficiency on Earth, and with a higher area utilization. So I hope I answered your question. Okay. I saw another one, and if there are more. Mm-hmm. Yeah, there's. So, in the middle and then the right. Go ahead. Yeah, go ahead. Yeah.
I was wondering about thank you, Professor, for the talk. I was wondering about the optical distribution network for the clocking. Do you encounter problems if you're stretching or distortion of the surface, like what you did for the deformation of the big thin phase array where you have to do calibration? Do you have
Yeah, I mean, that goes into the clocking network. I mean, so we have all of those local corrections include those corrections for the stretching, the skew of the clock distribution. So that actually makes the correction for that. So there are multiple layers of calibration. I talked about a couple of them, but there are multiple levels of self-calibrations that allows this to be able to recover that information. But yeah, that's a good point. That's actually a major problem. If you don't correct for these, your clock skew so to speak, is going to basically destroy a lot of your phase coherence and phase repeatability.
just wondering how you set like the bandwidth of like the return network. So because you wanted the time skew between them to be less than because
That's a great question. It really goes back to the fact that mechanics are much slower than electronics. Many orders of magnitude. So these things that are happening, especially on these structures, and my colleague Sergio's team has been analyzing this very accurately. Because the structures are large, the modes are very slow. They're like hundreds and 50 millihertz at the largest one. Some of them are much slower. So they happen very slowly. You don't need to do this very quickly. You just need to do this infrequently relative to the mechanical changes. Yeah? There was a question here.
Yeah, so how much energy, what's the focal size that you can get out of
For the space one? For the space one, if you put it in geosync, you can get it basically within like a 700, 800 meters diameter.
Oh, okay, so it's pretty big.
Yeah, for that. But if you are at a lower Earth orbit, the other not low Earth orbit, MEO mostly, medium mezzanine complexes or Earth orbit, because the LEO stuff is easier because the system becomes much smaller, but it loses some of its advantage because you have the similar day and night cycles. Because if you're in LEO, you're basically getting eclipsed by the planet a lot if you're close to the planet. MEO, you can basically make it up down to like 300 meters or something like that if you wanted to recover all of the power. But if you have an emergency situation, let's say for example, right, that you have these rolling carpet systems that basically you just roll open, and that becomes your generator. And yes, you may lose a fraction of the power. You may not recover all of it, but yeah. So it's basically between 300 to 700, 800.
The powers per square meter would be like safe?
Yeah, so the design, yes. No, by design, you can make this, because it's diffraction limited, so that's good. Physics is on our side until new physics emerges. It's not possible to get more than that, and we are designing the system right now for one sun equivalent of energy.
Okay, no more. So like it's not going to be a weapon?
Well, this cannot be weapon. No, yeah, good question. There are three questions I always get, and this is one of them. Are you building the Death Star? That's a good question. Now, this cannot be used as a weapon at the scale that it is. If you want to make it into a weapon, you have to make it about 100 times larger in area.
And my last question is it more efficient than a mirror array or a micro mirror array? Because that could also, and then you don't need to phase it, you just need to direct it.
Correct. No, that's it. The structural accuracy that you need for micro array, and this is interesting because we found this the hard way when we were doing. Let me see if I can find this picture. Yeah, this one. So when we were doing this, if you see here, I don't know if it's very clear. We have these concentrators, right? So this concentrator, there's a photovoltaic strip on the back of each concentrator that does that. So even getting those on such short distances to be using thin structures to have the level of precision that needs, because it's optical, much smaller wavelength and all those things, was difficult. So the problem with that notion that has been around again for a long time, the other notion is that put large mirrors, reflect the sun to the earth. But a mirror that can reflect it without spreading it too much and can maintain integrity, from a structural perspective, is very impractical. The benefit here is that we don't need any kind of precision on the photovoltaic side, because it's just like intensity. We are just getting the photons, converting them. And on the RF side, since the wavelengths are much larger, we can make all these corrections and adjustments. For an optical mirror of that mag size to be structurally made, it has to be either very heavy, for it to be rigid mostly, or it would not maintain integrity enough to be able to full concentrate.
But even on like micro mirrors,
but then you have to align each one of them, right? So that makes
you're aligning a lot of stuff.
no, but we're doing it electronically. The mass of mechanical alignment is significant, and also the cost is very significant, right? So that's the difference. There are people who are also talking about doing this with lasers, and that definitely is a weapon. No question. There's actually a company who tries to do that. It's a weapon. Yeah.
How long does it take the calibration algorithm to converge, the one with the Hadamard matrices? Because for applications on Earth, you're kind of spewing power in random directions during that period.
Yeah, you don't need to operate at full power, by the way, when you're doing that, right? Because you have large dynamic range. And it's actually pretty small. The other thing is that you don't run it too frequently. So that's the what we call the focusing algorithm. There's a refocusing algorithm, which basically is a computational calculation. It's done instantaneously. So once you find one focus, if you know the setting that puts the energy in at known XYZ, then in principle you know everything there is to know about the offsets of the phases, and there's a there's a vector calculation that you can actually do and translate from this point to any arbitrary point. You can say, if this is the setting I have for x1, y1, z1, and I want to now be at x2, y2, z2. It's a very simple forward calculation that you can do. I mean, simple. It looks mathematically messy a little bit, but yeah, it's forward. Yes.
Usually. So on the 70,000 phase array you had,
the one that we actually have. Yeah.
what is the phase resolution you needed from element to element? And what is the main challenge? What limits the size ultimately of these phase arrays?
So for something like that, generally for those kind of things, once you are below 10 degrees or something like that of phase accuracy, you're good. I mean, the gain becomes diminishing return. If you try to make your phase accuracy from 10 degrees to 1 degree, then you gain little. So anything below that is good for us. But remember, it's 10 degrees at 10 gigahertz is different from 10 degrees at 24 gigahertz. That's different from 10. Yeah, it's become smaller, obviously. Sure.
So for these non-planar geometries, so they were essentially planar because it was like a cylinder. So what if you want to have similar phase arrays on, let's say, spherical surfaces?
Oh, stretchable surfaces. So that's good. So what it's a great question. It's a differential geometry question, essentially, you're asking, which is that, the structures we had are non-stretchable structures. And you're asking, if I understood your question correctly, but I cannot take a sheet of paper and make it into a hemisphere without stretching it or compressing it, right? That's the Gauss's theorem, right? So what happens is that, but if you have stretchable surfaces, you can do that, and the computation actually works for that too. So it's doable, and the algorithm works for that. The only thing is that you have to just have a measure of local differential measurements of the stretching or compression of the surface. Yes, in the back.
Thanks for the great answer. My question was regarding the RF design. What major bottlenecks did you in RF design? How did you address them, especially under harsh conditions in this case?
Right. So there are several good questions in there. One is that, so in general, when you have a chip like this, you have like 17 PLLs on it, and you have 16 power amplifiers, and there's enormous opportunities for coupling and nonlinear dynamics of combination of power amplifiers and PLLs and all those things. And those are absolutely non-trivial things to solve. And it took us a few years to get them solved. In multiple spins and variations of the design. So in terms of space, one of the things that we had to do, and we learned a lot through this process, is that we had to go through the full space qualification. I have to go through various vibe, shock, all sorts of things, and you see the impact on the design of the circuit. But the good thing is that actually there's evidence, if you look at the literature, that small nodes of silicon, CMOS silicon, actually get better in space from a radiation perspective and all those things. And the reason is very interesting, because that's not the reason it's articulated. This is my hypothesis, why that's the case. My hypothesis, but I think I'm right, is that the active area of the transistor that's sensitive to damage becomes smaller, a smaller fraction of the total area of the chip. So when you are in a small feature-sized node, what happens is that you get there's less chance of something hitting it and damaging it because it's just smaller, it's cross-section. But there's data on that, and there's literature on that. But there's a lot of interesting things when you want to send to space, and some of them are, especially if you come from a background of IC, like IC design or chip design, like I was coming from. You're used to fast turnarounds. You're used to, okay, well, do this, and these are the kind of things. And Okay, yeah, either you measure this or not. And no, it's not. I mean, the things that break and things that you spend the most time on when you send something to space are sometimes the most basic things. And some of the things are really weird and interesting. It's very interesting to see that you put something that you put together this mechanical structure that supports your system, and you put it in a vacuum, and you see the screw starting to unscrew in front of your eye. And the reason is that there was some air that was caught behind the screw, and now that the pressure is going down, it has to apply sufficient pressure to kind of start the screw unscrew. And you say, oh, okay, I don't know what's going to happen next. And they make special screws, for example, for that as a simple example, that has a little hole in there, like in the middle, so the air kind of also gets sucked out. There are all sorts of interesting things that happen. And I don't know if you know about tin whiskers, for example, right? So tin, which is what is used in lead-free solder, under vacuum, starts deforming. And instead of being just remaining like a nice round ball, it starts forming these whiskers that kind of come out of it. And all sorts of interesting things happen as a result of that. So those are two funny examples for you. Yes?
So, increasing frequency helps us with decreasing the size of the RUGU. But I'm also assuming at higher frequencies the DC to RF conversion losses are going to be higher.
Right.
So
there's a sweet spot.
Right. Oh, so that is a sweet. So is 24 gigahertz that spot, or are you saying
it's close? It's close. I mean, the actual spot, if you pick it, then you have to deal with other things. I mean, just like the numbers, some arbitrary frequency that you just 24 gigahertz on ISM band. So that's a good thing about it. Any more questions?
I'll make a quick comment about, putting these things on Earth in the desert. Everyone assumes the desert, it's dead, you can do anything you want, but it's actually a living environment. When you put solar cells, kilometers, tens of kilometer solar cells, you destroy a whole ecosystem.
And that's correct, because of all this, like also you block the light and everything. And the other interesting thing about this receiver is that they can be translucent even, and they can be much smaller, but even they can translucent. And the other part that people also ignore is that the footprint and the cost of the transmission line. If you want to power, let's say, a remote village that's like several hundred kilometers away from the nearest power station, just the footprint, the land footprint of that transmission line system is not insignificant. The cost of it is not insignificant. Now, or if you say, no, I'm going to put photovoltaics, and forget about this, even like whatever happens underneath it, you need storage. The cost of storage, all of those things are things that... So we did actually a pretty detailed analysis of this thing. We did a full techno-economical analysis, which we just recently published in Joule. And then it came out, and if you look at it, you will see the cost structure. So when you put all of these things into account, all of them into account, the cost structure we think that we can eventually reach is to provide levelized cost of electricity, LCOE, of about 10 cents per kilowatt hour, with everything included. And the details are provided in the papers. You can see our analysis, you can see the numbers and see where we've made a mistake.
And how does that compare with like existing renewable energy?
It's definitely on par. But the other thing is that also you have to, there are these additional costs, right? For the storage cost or the transmission cost that needs to be taken into account. Now, when I first thought about or was looking at it, my first reaction was the robot's reaction. But the more you put the numbers down, you say, well, yeah, maybe there's a way to do this. Maybe there's a reason to do this. But again, it's a very difficult problem still. There are a lot of challenges to be overcome if you want to solve this.
So do you feel like scaling from 70,000 to, let's say, 100 million elements, which is what probably you need, are there like any fundamental bottlenecks, or is it just like an engineering and economical challenge?
No, there are challenges of timing, for example. I don't know if it's fundamental, but they are very hard. There are the challenges of just the scaling. I mean, when we went from, anytime we went from, like, let's say tens to 100, there were new challenges. When we went from 100 to 1,000, there were new challenges, a different set of challenges. I mean, this is roughly, it has nothing, I mean, it just happens to be coincident with the number of fingers we have, like these factors. But just like when we went from 1,000 to 10,000-ish, there was another set of challenges. I'm thinking about those. And then when we get to close to 100,000, which is what we're talking about, then it's a different set of challenges that happen. So my rule of thumb is every factor of 10 is a new set of challenges. And flexible is definitely another, at least another factor of 10 of, equivalent of one more factor of 10. But I mean, the thing is that there's something to be said about like 70,000 synchronized phased array elements working simultaneously together, right? And delivering a lot of power.
All right, maybe before you go to the slide that showed the movie, so people can get the links. Want to learn more and be entertained? I'm sure.
Yeah, this was actually premiered on Monday. So when they introduced it, they said, well, if you think this is the only movie that will have the name of 3 professors on top of the flyer, so I don't know.
There was a birthday movie, the one about downloading your brain, I forgot.
Oh, okay, so there might have been some other ones. Okay, good to know. Okay.
I wasn't involved.
Okay.
Thank you very much.
Thank you.
Great talk.
Oh, thank you. Thanks for everything. Thank you for listening. Thank you.
Really entertaining.
The impact of GPL and